In this lesson, we'll start moving beyond image classification, where we take an image and output a probability distribution over the classes or categories. Here, we'll start talking about other computer vision tasks, such as image segmentation or object detection. So far, we've only covered image classification. We now know how to take an image, feed it through a convolutional neural network to both extract features as well as classify it, and output after softmax a probability distribution over classes. But this relies on the object being most of the image. Other tasks we may want to perform is semantic segmentation. Here, we want the same probability distribution, but for each particular pixel. Note that we're not really distinguishing instances here. That is, we don't know that this particular pixel is car 1 and a different pixel is car 2. All we know is that these pixels are cars. Therefore, we might want to do instance segmentation, where we actually have a unique ID for each instance as well. Another task is object detection. Here, we're not looking at individual pixels, but rather looking at bounding boxes. That is, for each object in the scene, we want a bounding box around that object, and again, a probability distribution over the categories. And these are all not independent. Sometimes networks can combine to estimate all of these, or some subsets of them. Let's talk about image segmentation. Given an image, we really want to output another image. That is, each output contains the same width and height, but a class distribution per pixel. This is more generally referred to as an image-to-image problem. That is, we have an input tensor with a width and a height and a number of channels, typically 3 for a regular RGB image. And then we want the output to essentially be another tensor with the same width and height because we're trying to classify each pixel. And the depth is the number of categories. Here's a depiction of what that looks like. Again, we have a width, a height, and here are 3 channels for red, green, and blue. And then we want the model to output another tensor with a width and a height, with the depth being the number of classes. Now, this is drastically different from what we've done before. Thus far, we've applied a convolutional neural network to an image, and this creates downsampled feature maps at the end of the convolution layers. And these convolution layers are then fed into fully connected layers. The convolutional neural network performs some dimensionality reduction, both through convolution operations and also through pooling operations. The question is, how can we perform upsampling here? We want to still extract meaningful, abstract, high-level features. However, we want to then convert those features into some estimate for these tensors. One reason fully connected layers are not applicable to segmentation problems is that they throw away explicitly spatial information. That is, the output of fully connected layers is in the form of vectors, and so they're no longer spatially organized, similar to how the images were. Now, the neural network can still retain some spatial information, for example, by learning weights that are specific to different regions of the output feature maps at the last convolution layer. But it's certainly not an explicitly spatial representation. And so one idea is just to get rid of fully connected layers altogether. That is, perhaps we can devise a fully convolutional neural network that doesn't have fully connected layers and maybe still output something resembling segmentation outputs. So it turns out that you can convert fully connected layers into a convolution operation. This is because convolution operations are very similar linear operations to fully connected layers, as we've discussed before. And what we can actually do is just take the fully connected output nodes and reshape them back into the same sizes. This can be seen as a convolution operation because we can just have the kernel be the exact size of the input. That is, if you see here, there are some sets of output feature maps at the end of the last convolution layer. And then we'll have kernels, which are shown in blue, with the same exact size as that input to the next layer. And so rather than have a fully connected layer, we'll have a fully convolutional hidden layer where each kernel is essentially representing each output node. This can be thought of as just taking that kernel and again just dot producting it with the entire input. And for that, we get one scalar output. And so this is exactly equivalent to the Wx plus b fully connected layer that we've learned about. And we can do this for other layers as well, not just the ones that are immediately after the last convolution layer. And again, we have one kernel per output node here. So mathematically, the representation of a fully connected layer or a convolutional layer where the kernel is the same size as the input are equivalent. And so you might ask, why would we want to do this trick? So it turns out that this allows us to be no longer dependent on a particular input size. And we'll show how this is useful for segmentation. For example, suppose that we have an original input size, here 5 by 5 image, and we have a kernel that we've learned, a 3 by 3 image. And this results in an output of size 3 by 3. And so when we have a fully connected layer after this, or after we've converted it into a fully convolutional layer, we'll have a kernel that's exactly the size of this output. And so we'll have a fully convolutional layer kernel that's dot producted with that to produce one output node in the fully connected or fully convolutional layer. And then we can have multiple of these if we want multiple output nodes. It turns out that if we feed it a larger input, as we know, since it's normal convolution, the output map at the last convolutional layer will be bigger. This is because, again, the convolution operation is defined by the striding operation, and it has nothing to do with a particular input size. All we're doing is striding this kernel across the input to get an output map, and it doesn't really matter what size the input is. And so if we retain the same fully convolutional layer as before, we'll now have a smaller classifier with respect to the new larger output size. And so you could see that now we'll have a larger output. We'll have an output with 3 by 3 from this fully convolutional layer kernel being strided across this new larger input. This matters because we can actually just see this as striding a classifier across the larger outputs. And so we can actually use this to get a segmentation output. Specifically, we can take a smaller size, let's say the normal ImageNet classifier sizes, which are typically 224 by 224, shown here where it says original sized image. And we just learn a normal convolutional neural network. It can have normal fully connected layers. And then we now feed it in a larger image, and we convert the fully connected layers into fully convolutional layers. That is, we'll just reshape those weights to be of the size of the inputs. And so when we run this larger image through the convolutional neural network, we will get a larger output at the last convolutional layer. And then we'll stride this original classifier that we learned, and we'll get multiple outputs. And this corresponds to applying the classifier at different positions in the image. And again, this is a very segmentation-like output. That is, for each position in the image, we get an output of what the class label is. And of course, the size of this heat map that's shown here on the right is going to be dependent on how much you're enlarging the input image size. If you only enlarge the input image size by a little bit, you'll get a very tiny heat map. But if we use much larger images, then we'll get much larger heat maps. And then we'll essentially get a segmentation output. That is, for each pixel in the image, we can get what class or category is in that image. Now notice we don't quite get every pixel here since it's still downsampled. The output is still going to be smaller than the actual image. So you could do various tricks. For example, you could upsample this. So you could just apply normal image processing methods to take this heat map and resize it to the larger image size. And then you will get some probability distributions across the original image. Now, the fully convolutional neural network that we devised for segmentation is perhaps still not ideal, even though it gets us some coarse segmentation output that we can then upsample. It's still not going to be that high resolution. And also, we have to feed in much larger images to get that output. Instead, we can try a different idea. Here, we might think about how can we devise layers that actually perform upsampling rather than downsampling. By that I mean, traditionally, when we looked at the convolution and max pooling layers, these resulted in smaller images at the output. And so we continue to apply this and got small feature maps by the end. This is called an encoder. We're encoding the image into highly relevant, abstract features that are important for whatever task we want. And so we could try to think about how to develop what's called a decoder. That is, we want to take in those small feature maps, which represent very important features, and try to use them to upsample, that is, to generate more and more high resolution outputs that eventually are the size of the original input image. This is called an encoder-decoder architecture, and we'll see these both in computer vision as well as in natural language processing and other applications. Now, one question is, how do we actually do this? And it turns out we can actually do some sorts of inverses of the traditional layers that we had. Specifically, rather than a convolution layer, we can have what's called a transposed convolution, or loosely termed deconvolution. And rather than have a max pooling layer, we can have an unpooling layer that does something slightly similar but results in a larger output rather than a smaller output. Now let's take a look at the max unpooling first. If you remember, max pooling has a window size, let's say 2 by 2 in this case, that you stride across some input image. And for each window, you take the max element and put it in the corresponding output. So if your input looked like this, then the maximum is 200, and that's the value that you would put in the green output square. And if you remember, during the forward pass, you have to remember which element was the maximum in order to propagate gradients properly during the backwards pass. Now in unpooling, we want to do the opposite. That is, given a smaller input, we want to generate a larger output. And so we might actually do the opposite of what we did for pooling. That is, we might stride pixel by pixel in the input, and for each of those pixels, generate a larger output. Again, let's say 2 by 2. And so the only question is what the location should be for that particular input pixel. And one idea is just to remember the max element in the encoder. That is, we're going to put for each window back the element in the position that was the maximum when we did the encoder. And so here, for example, we remember that location 2, 2 is the maximum. And so we essentially put back that value into 2, 2 across a 2 by 2 window. And we fill the other three values here as zeros. And then we do the same thing again. We move over one pixel in the input and we generate again another output window where we put that value into the same location that was the max in the encoder. Let's take a look at a more explicit example. Suppose that we have this particular 3 by 3 input X, and what we want to do is perform max pooling for a 2 by 2 window. And so the first window, the first 2 by 2 on X will be 120, 150, 150. And so the maximum is located at 0, 1, that is the 150. And so that's the first element of Y. And similarly, we'll stride this 2 by 2 window in the 4 locations on X. And we'll remember the particular locations of all the maxes for each window. In the actual decoder stage, we'll want to take a small input, in this case a 2 by 2, and make it larger. And what we're going to do is again iterate across every single value in this input and stamp it across a 2 by 2 window in the output. And so we'll, for example, take this 300 and have it located in the 2 by 2 window in the same place where the maximum was in the encoder. That is, the 150 was in location 0, 1, and so we'll put the 300 in the same location, and we'll put zeros in other places. Now, just note that there's other ways to do this. For example, we could stamp the 300 across the entire window in the 2 by 2 region, but typically this is what's done. Now, similarly, we'll continue to go to the next location, which is the 450, and we'll again stamp the 450 in the location of the maximum. In this case, the 450 location for the maximum was the same location, that is 0, 1, and so we'll put that in the output. And again, because the 300 was already there, we'll just sum up the contributions. And so for windows that overlap that have the max indices in the same exact spot, we'll just add up the contribution. And so on. We'll continue to do this for the 100 and the 250, and this is what the result will look like. And again, there's going to be many zeros around because there's only going to be a few locations where the max indices were chosen in the encoder stage. Now you might wonder, what does it mean to have a pooling and an unpooling layer correspond? And so here what we're going to do is we're going to have an encoder which may consist of multiple convolution and pooling layers, except that we'll have an encoder and a decoder that are symmetric. That is, the architecture of the decoder will be completely the reverse of the architecture of the encoder. And so what we'll have here is essentially an architecture that allows us to do unpooling across the layers by remembering the locations of the corresponding pooling layers. One issue with max unpooling layers is there are no learnable parameters. So we're not really learning how to upsample. All we're doing is taking the max indices in the encoder stage and applying them at the decoder stage to upsample images. The next question is, can we actually apply a similar operation as a convolution where you have a learnable kernel and perform upsampling? So if you remember, a normal convolution, again, has an input and a kernel with a particular size, let's say 3 by 3, and that kernel is strided across the image. And that image patch corresponding to the particular location is dot producted with the kernel to get the output. What we can perform is something called transpose convolution. It's also known as deconvolution, although that's not a great name because that means something very specific mathematically that's different from what we're doing here. It's also known as fractionally strided convolution. The idea is, again, we're going to do something similar as what we did for the max unpooling layer. We're going to go pixel by pixel in the input, and for each pixel, generate a larger output. Except here, we're going to be multiplying that input by some learnable kernel. Rather than dot producting the kernel across the image patch, what we're going to do is, again, the opposite. We're going to take one input value here in location 1, 1, and we're going to actually multiply that one value by each of the values in the kernel. And so that corresponds to essentially stamping that kernel times the value across the 3 by 3 location here. And then we'll do something similar across the entire output. So again, let's take a look at an explicit example. Suppose that our input x is this 3 by 3, and we have a particular kernel. And there's some values here, but again, these are the learnable parameters. And so what we'll do is we'll iterate for each value in x and try to generate a larger window from that one value. And the way we'll do this is we'll multiply that value, for example, starting with 120 with the kernel. So here we'll get 120, negative 120, and then 240 and negative 240. And we'll essentially stamp that onto the output. And so that's going to be on the upper left. We'll move over to the next value, which is 150. And again, we'll stamp that 150 multiplied by the kernel, where we'll have 150, negative 150, and then 300 and negative 300, and we'll stamp that. And again, the areas where these windows overlap, we'll just sum the values. And then you move on to all the values in X, and we won't show the results of all of that, but you can try to work that out. Because we have a symmetric encoder and decoder, we can actually do two variants of this. The first is what I mentioned earlier and have the kernel learned. That is, the kernel values will be learnable parameters and we can backpropagate through them. The other alternative is actually to not learn the kernels at the deconvolution or decoder stage. What we can do is take for each deconvolution layer, take the corresponding mirrored convolution layer in the encoder, and then take that kernel that was learned or those kernels that were learned and flip them 180 degrees and then apply them in the decoder. So again, these two variants exist, but typically the kernels are learned. Because we're using a normal convolutional neural network for the encoder, we can actually use transfer learning here again. That is, we can train a convolutional neural network for image classification, let's say on a large data set such as ImageNet, which has over 1 million examples and 1,000 object categories, and optimize those weights for the image classification loss. And then we can take those learned weights and copy them to the encoder. and we can mirror the architecture for the decoder and then initialize those randomly. And then we can jointly optimize the encoder and the decoder given ground truth if we have it for a segmentation task. Note that here we'll also use cross entropy, except that we have a probability distribution over the categories for each pixel. And so we'll have that many losses that all get into the optimization during backprop. You can also use a lot of the ideas that we had for image classification. For example, residual neural networks use the idea of skip connections. We can actually do this for encoder-decoder networks. This is what's called a U-Net. Here, it's the same thing as what we had before. We have an encoder part, and then some bottleneck features, and then we have an decoder part. Except here, we're not using only the bottleneck features. We can actually have skip connections where you take the feature maps from various parts of the encoder and actually concatenate them with various parts of the decoder. And so here, what you're doing is combining information both from the encoder at multiple scales, that is, at multiple resolutions of information, because the feature maps get smaller and smaller, and you're combining that with the upsampling that we do for the decoder. This is a very successful architecture for various types of segmentation tasks. So in summary, there are various ways to get image-like outputs, or actually tensors of a width and a height and a depth. And we can perform various tasks such as image segmentation using these methods. Fully convolutional layers that take fully connected layers but convert them to these convolutional style layers really apply the striding idea to our classifiers. And this allows us to support arbitrary input sizes, where the output size actually depends on whatever input size we feed it. We can also have various upsampling layers that actually increase the size over the input. And combining all these into encoder-decoder architectures is a very popular way to perform various image-to-image tasks, segmentation being one of them. In this lesson, we'll talk about object detection, and specifically single-stage methods that take images and try to directly output a set of bounding boxes with predictions for each of them. In object detection, we're given an image, and we want to output a list of bounding boxes with a probability distribution over the classes for each box. There are several problems here. First, we have a variable number of boxes. We don't know how many objects will appear in these images, and so it could be as little as 0, or it could be as many as thousands or more. Second, we need to determine candidate regions, that is, positions and scales of the different possible object locations in the image. And again, we can make architectural changes in order to make this happen. For example, we can use the same idea of fully convolutional neural networks. We can use some ImageNet pre-trained model as the backbone, for example, taking in a 224 by 224 image, and then we can feed in a larger image and classifications for different windows in the image. And again, here, we're only getting the probability distribution over the classes at the end. However, we're not looking for a probability distribution over the classes for each pixel. What we want is actually an estimate of the bounding box, that is, where the upper left corner of this object starts and the width and height of that object, which is one representation for a bounding box. You can have 4 numbers representing this, an x, y, width, and height. And so what we can do is have what's called a multi-headed architecture. That is, we can have a convolutional neural network that outputs a set of feature maps at the end of the last convolutional layer. And then we can have one part, which is another fully connected layer, or if we want to, we can convert it into a fully convolutional layer. And that part can predict, again, the class labels. But we can have another branch of the network that takes the same feature maps and has a new set of fully convolutional layers. And here we're predicting as a regression problem the 4 numbers, x, y, width, and height. What we want to do is have this bounding box fit across the object in a tight manner so that it precisely tells us where the object is. And one of the key things, and again, this is the key advantages of deep learning, where we can tie together things in a joint computation graph, is that we're going to have shared features here. That is, we're optimizing the convolutional neural network up until the last convolution layer for both of these tasks, the classification task and the regression task for bounding boxes. That is, we're not just going to have one loss function, we're going to have two loss functions. And by the way, for example, for regression, we can use standard ones such as mean squared error. And typically, we'll have, just like regularization, weights for each of these loss functions. So we'll have a weight for the cross entropy loss and a weight for the mean squared error loss. And again, these will be hyperparameters that can be tuned. And so in this multi-headed architecture, we can actually apply it to give us object detection. And so this is what it will look like. We'll actually feed in not just one image, but multiple images of the same thing, but at different scales. That is, we'll take the same image and either downsample or upsample it using traditional image processing methods. And we'll feed all of those into the fully convolutional neural network. And for each of those, it will give us across some gridded pattern a set of predictions for each grid element, which has classification, probability distribution, as well as regression to a bounding box that is x, y, width, and height. And so what you'll notice here is, first of all, that it's gridded, again, because of the fact that we're using a fully convolutional neural network, and it results in small feature maps at the last convolution layer, and we're essentially striding a classifier or a regressor across that small feature map. And so by definition, it'll essentially lead to grids in the input image when we figure out what receptive field each of those convolution feature maps have. And another thing you'll notice is that this may be, again, low resolution. Similar to how we talked about before, the output is really going to be a set of heat maps. And so this may be too low resolution for things like object detection. There's going to be a bunch of tricks in this paper that you can look at that actually tries to make this higher resolution outputs, and I won't go through those. Another thing to mention is that you'll have lots of different bounding boxes, and many of them may have low probabilities for different objects, so you might be able to filter them out. But in the end, you'll have multiple bounding boxes, especially around actual objects. And so, again, in computer vision, there's a whole set of techniques that take a lot of different predictions in similar locations, all with probabilities associated with them, and combines it into one or a few actual boxes. This is called non-maximum suppression. And again, I won't cover this because this is traditional computer vision, not really deep learning. Over the years, a number of refinements have been made over these architectures. For example, the single shot detector, or SSD, has a very similar grid idea. That is, we'll impose a grid over the input image. And this corresponds to some grid over the convolutional feature maps at the last convolution layer. And then for each position in that grid, we'll actually estimate some set of bounding boxes of particular shapes or aspect ratios. And again, this is a pure hyperparameter. And in this case, there's 4 different bounding boxes here as dotted lines that we estimate. And then for each of those bounding boxes, we estimate a refined bounding box, x, y, width, and height as an output of a neural network, as well as a confidence that is a probability distribution over classes. And because we have a fixed number of these, because the grid is a fixed number of elements and each grid location has a fixed number of bounding boxes around which we estimate this, you can actually just have one big neural network that outputs this directly. And so there's various tricks that you can use to increase the resolution of this, and I won't go into those, but you can also apply the skip connection or multi-resolution idea as well. So here you'll notice you actually estimate these across a number of bounding boxes in different layers. You don't actually impose this grid on one particular feature maps, but actually impose this on multiple feature maps across the depth of the network. And so closer to the input, you'll have higher resolution ones since the larger size outputs allow you to do that. Whereas deeper inside the network, your convolutional output maps are much smaller. And so your predictions are going to be smaller as well. And then you combine all of the predictions that the neural networks makes across all of the different layers, and you then perform non-maximum suppression. And in this case, if you notice, you'll have 8,732, again, a fixed number of predictions. And you can apply NMS to that to produce a small number of bounding boxes, for example, around the cat and the dog. And so there's other architectures such as YOLO, you only look once, that has a similar idea where you have an input image and you want to essentially make predictions for each gridded location across those images or across the feature maps. And in this case, the only difference is that we're going to use some customized architecture. SSD actually uses a convolutional neural network backbone that's pre-trained on ImageNet, such as ResNet, for example. But here there's a custom architecture that eventually leads to a fully connected layer, and again, making predictions for a fixed number of grid locations. And there's various trade-offs between accuracy and computation across all of these architectures. The way we evaluate these, again, is through large data sets. And in this case, rather than ImageNet, there's a data set called COCO, which has a lot more objects per image, whereas ImageNet typically just has one. Here we have somewhere on the order of 3 to 7 objects per image. And there's a lot more data and a lot more categories, in this case, 80 compared to prior object detection datasets, such as Pascal VOC. And here you can see a distribution or histogram across all of these different 80 categories. There's also various ways to perform evaluation. In this case, with bounding boxes, the metrics are much more complicated. So some methods that we use, for example, is to extract for each bounding box that you detect some intersection over union with the closest ground truth. And so this literally means you take the intersection of the two bounding boxes, so that area that intersects, and you divide it by the union of the bounding box. And this gives you some element of how good the fit is. And you can only keep those with really good fits, for example, intersection over union greater than 0.5. You can then calculate precision recall curves across these classification using different thresholds on the probabilities. And you can actually boil this down into one number by performing what's called average precision. That is, you take the precision at a recall of 0, 0.1, all the way to 1.0. And so you'll have 11 numbers here, and you'll have average precision that essentially averages over these 11 numbers. And then you can do this for each category. For example, out of the 80 categories, you could do this for each one. And then you can average the average precision over all of the categories. And this is called mean average precision. And here, higher is better. And so over the years, many different architectures have been developed. I can't possibly go through all of them, and new ones come out every month. And so there's lots of different trade-offs that you can make. Typically, these represent on the x-axis some form of computation complexity, either flops, floating operations per second, or FPS, which is frames per second. And then on the y-axis, you could show the mean average precision. And as you can see, again, there's various types of architectures, such as the YOLO one, which have pretty good trade-offs here. There's a new variant called PP-YOLO, which came out in 2020 that has a pretty good trade-off. You can go up to 130 frames per second on a good GPU. And then there's also new architectures, for example, based on EfficientNet called EfficientNet. In this lesson, we'll talk about two-stage object detection. Unlike the previous ones that we've talked about, here we're going to have two stages. One stage that actually gives us regions of interest, that is, parts of the image that might contain an object. And then we'll have another stage that actually performs classification and regression to better bounding boxes. Instead of making dense predictions in a grid across an image, we can decompose the object detection problem instead into two steps. First, we can find regions of interest, or ROIs, with object-like things. That is, regions that have a high probability of having some sort of object in them, as opposed to being part of the background. We can then classify those regions and refine their bounding boxes. Specifically, we can take each region of interest, that is a crop in an image, we can resize it to take whatever size that is input into the convolutional neural network. For example, a pre-trained ImageNet model. And then we can obtain predictions. We can do this for a batch of data and then backpropagate to optimize the model. Now, there's a question of how we find these regions of interest. In some sense, this is the biggest problem that we have for object detection. And it turns out we can actually use unsupervised, non-learned algorithms to find these candidates. These were developed before the resurgence of deep learning. Specifically, we can perform things like unsupervised segmentation of images. That is, we'll group pixels together in order to find semantically coherent pieces of information in the image that may correspond to objects, or they may be things like patches of grass and so on. And we can do this at multiple scales. That is, we'll take the same image, resize it to be bigger and bigger or smaller, and then extract these segmentations. And then we'll combine all that information to get a set of candidate bounding boxes, which may be around some objects. For example, this algorithm shown here is called selective search. Now, there are several downsides to this algorithm. First, it's really slow. It takes 1 or more seconds per image to extract these bounding boxes. Second, they return thousands of boxes, mostly of background, or at least parts of objects, not the whole object itself. Now, they do return scores typically, but the scores are not very good. In other words, in order to get most of the objects, you have to have a pretty low threshold, and you'll still end up getting at least hundreds or thousands of boxes. Another problem with this overall approach, that is finding candidates and then feeding each candidate through a CNN, is that this is going to be really slow. Again, if we feed hundreds of images or crops within an image into a CNN, then it's going to take a long time for just one image to process. If you think about it, the biggest problem here is that we're wasting a lot of computational resources actually computing the exact same thing, because we're taking a bunch of different crops within an image, and a lot of these crops are actually overlapping. That is, they have parts of them that overlap across the boxes. And clearly, across thousands of boxes, you'll have lots of overlap. And if you think about the way convolution layers work, as you're striding a kernel across these images, you're actually redoing the computation. For example, for the parts that are overlapping, you're computing the dot product with the kernel for the same piece of image with the same kernel. And so this is wasting a lot of computation. And so what we can instead do is take the image and feed it through the convolution parts of a CNN, that is up until the last convolution layer before the fully connected layers. And we'll only compute this once. And the output of this will be a set of feature maps. And what we can do is, given a crop or a region in an image, we'll actually just find the mapping between the pixels in the image and exactly what pixels in the feature maps they affect. Remember, we can compute this. We know, given a feature map pixel, what is its receptive field? That is the set of pixels in the input image that is affected by it. And so we can just do this. We can take the crop, compute the specific region within the feature maps that that crop corresponds to, pull out essentially those strands of features, and then feed that into the fully connected layer. So in doing this, we're reusing the computation, and we're doing feature extraction only once. There is one problem with this, though. If you have different regions of interest in the image that have different sizes, they'll correspond to different sizes in the feature maps. And so, since fully connected layers require a fixed input size, this is an issue. And so what we'll do is something called ROI pooling. And this is part of an algorithm that's called fast RCNN. It's similar to RCNN, where we're taking regions of interests and feeding them through a CNN, but it's, again, doing the trick that we just described, which is computing the convolution layers only once. What we're going to do is take whatever sets of feature maps and only take the part that corresponds to the particular crop in the input space, and we're going to grid it. So we're going to have a fixed number of grid elements. In this case, we'll have 4 by 3, so we'll have 12 grid elements. And for each of these grids elements, we'll just take a max operation. And so here we could see the upper leftmost grid element may have multiple values in that little yellow box, but we'll take the max, and maybe that's 120. Similarly, we'll do this for all locations. If you notice, what this does is it actually equalizes the input size. That is, because we're fitting a fixed size grid onto the feature maps, the output will be fixed size. And now we can feed them into a fully connected layer. Notice that you can backpropagate through this, similar to any max pooling type layer. So now we can train this model end to end using backpropagation. That is, we have an image, we compute the convolution parts of the CNN, we extract some feature maps that result from that, and then we have a set of bounding boxes or ROIs that come from whatever other algorithm that's not learning based, and then we extract those feature strands that correspond to that, and then we feed those to ROI pooling and fully connected layers. And again, because we can backpropagate through the ROI pooling as well as all parts of this process, we can actually just optimize the entire thing. We can backpropagate all the way to the features and optimize them as well. And so this is called the fast RCNN algorithm. Now, there's a follow-on algorithm called faster RCNN. The idea here is to make use of deep learning to do everything. That is, rather than have a separate non-learning based algorithm that gives us these regions of interest, we'll instead use what's called a region proposal network, or RPN. And this RPN will take the same features that the convolution parts of the CNN extract and will estimate a set of bounding boxes along with what's called an objectness score. That is a probability that there is some interesting object in there, as well as potentially a refined bounding box. That is the 4 numbers for bounding box refinement. And so what we can do is have the region proposal network essentially regress from the features to a set of bounding boxes, and then we can select the top k of them, that is with the highest probability of having some object in them. And then do what we did before. That is, for each region, perform ROI pooling on the same features, and then essentially perform classification and regression again. So if you note here, now we'll have 4 losses. We'll have a classification objectness score for the region proposal network, which will also have bounding box regression loss. And then at the end, we'll have another classifier that classifies not between object or not object, but across however many categories we have, and then another bounding box regression or refinement. Note that some parts of this actually is not differentiable. For example, it's not clear how to find the gradients of the loss with respect to the bounding box coordinates. For example, if you think about moving the bounding box a little bit, because you're changing the weights that map the features into the bounding box, that is the regression network. It's not clear how your loss changes because you're actually changing the bounding box itself, which means you're taking different inputs, different pixels, and then those get fed into ROI pooling and you're performing classification. So we can't really get this gradient. So there's a whole lot of details and complexity that I won't go through, but you can check out the paper in order to alleviate this. One way to do this is just to alternate the training. That is, train the RPN and then train the classifier and then alternate these 2 steps. Now we still have the problem that the region proposal network, or RPN, can't really have a function that regresses from the feature maps to an arbitrary number of boxes. And so here we'll use the same trick that we used for YOLO and SSD. That is, we'll have a grid on the feature map, which is actually a grid also on the input, again, because of receptive field calculations. And what we'll have are anchor points, which are centers of these grids. And for each anchor, we'll have k anchor boxes stemming from them. These are boxes of various sizes and shapes whose centers are in this anchor center. And again, the size and shape and number of anchor boxes that you have are all hyperparameters. And so here we'll learn a function that directly regresses from the feature maps to, in this case, a 256-dimensional hidden vector, and then regresses to 2 times k scores. It's 2k because, again, we're classifying between 2 classes, object-like or not object-like. This is called the objectness score. And then we'll also regress to 4k coordinates. These are, again, the 4 coordinates per bounding box where we're refining the object bounding box, because these anchor boxes might actually not perfectly overlap on top of the objects that we care about. And so again, this allows us to explore boxes of various sizes and scales along with objectness scores and refined bounding boxes, and doing this in a way where we're not outputting a variable number, but rather a large number. And then we can take the top objectness scores, the bounding boxes out of all these that have the top objectness scores, and take the top n of them. That is, we'll filter out the rest that have low objectness scores. And then these will be the regions of interest that are fed to the other branch, which is the classification branch. There's other advances that have been made since, and I can't cover all of them. Suffice it to say that there's a large number of different architectural changes that you can make. And you can also combine it with various other types of computer vision tasks. For example, Mask RCNN performs the same thing as Faster RCNN, except it also has a mask that it learns, that is a segmentation. So for each region of interest, it not only tells you what is the object that is in that bounding box, but it also tells you exactly which pixels within that bounding box actually touches the object, because there may be some background pixels, for example, grass and so on. And so over the years, there's been many algorithms that have improved the mean average precision of, for example, object detection and segmentation in data sets such as COCO. So on the lower right, you could see again a nice graph. This is from a website called Papers with Code, which tracks the state of the art across various deep learning and other AI machine learning tasks. And here you could see it progressively increasing, where Mask RCNN is actually not that high. You can get approximately 40 to 45% map. And then EfficientNet, which is a new architecture based on EfficientNet, which is a classification architecture, can get much better. And again, there's a large space here between computation and accuracy as well. In summary, two-stage object detection methods decompose the problem into first finding object-like regions and then classifying them. At both steps, bounding boxes are refined through regression. And so for faster RCNN and other variants where the region proposal network is also learned, we will have at least 4 losses: classification loss for objectness and then a bounding box regression at the region proposal network. And these candidates that are highly scored will then be fed through the classification part, which will again output classification, but in this case across the categories, and then another regression to further refine the bounding box. And if you'll notice, actually, we can keep adding various losses, such as Mask RCNN has additional losses for the foreground background mask. And these algorithms also have a lot of hyperparameters. So you'll see 30 or more hyperparameters. So these systems are certainly not easy to work with. They have a lot of complexity. These methods are slower than methods such as YOLO or SSD, but they tend to be more accurate. However, of course, the landscape is constantly changing, so anything I say here about which is better might be obsolete by the time you see it. And one of the interesting and key things that we'll see is that transfer learning can be used to pre-train the trunk, that is the convolution part of the CNN. And so we can leverage both lots of data for classification tasks, such as ImageNet, to pre-train those weights. And we can also use better and better backbones in order to leverage whatever state of the art comes out. And so these algorithms are not really specific to what backbone or trunk network that you use. That is the convolution parts of the CNN. You can use any one, and as newer ones that are better come out, you can just leverage them and plug them into this same algorithm.